Hello everyone. Thanks to everyone for watching this video. My name is Qidang. I'm an architect and engineer. Today's video is titled Strut and Tie Models, and it is going to provide you the fundamentals of strut and tie models and also the mathematical derivation of truss layout optimization. I am going to give you an overview of what I'm covering in today's video. First at all, it is a bit of background to the topic, and then focus on the truss layout optimization and the work examples before wrapping up with conclusions. Reinforced concrete is a complex composite material that continues to challenge a lot of researchers attempting to describe its behavior with mechanics-based models. The analysis of shear in reinforced concrete members is based on the so-called truss analogy. The truss model helps to understand how forces are transferred throughout a structural member. The equivalent truss model is identified on the basis of the crack pattern that appears when the member is loaded. The crack pattern helps to describe load transfer in the member by means of forces that are concentrated in compressive struts and tensile loaded bars. The truss analogy proposed by Ritten-Moshe for the calculation of shear reinforcement in reinforced concrete members is the oldest and well-known example of reasoning by means of strut and tie models. However, the method is also very well suited for the design calculation of compact structural members, such as foundation slabs supported by piles, cobbles, D-beams, walls, and anchorage regions in pre-stressed members. Designing members by means of the strut and tie method belongs to the domain of the application of the plastic design philosophy, and more in particular to the domain of lower bound methods. Indeed, the design is based on a truss model in which acceptable stresses are not exceeded in the members of the truss, and is thus based on a statically acceptable system, which may transfer the loads with sufficient safety. The philosophy described above is the one of the lower bound methods for plastic design in ultimate limit state. According to the lower bound theorem, the structural member doesn't fail if for the imposed load combination. A stress distribution can be identified for which equilibrium is guaranteed, and the threshold for plastic behavior of materials is not exceeded. Every structural member can be subdivided in so-called B regions and D regions. B stands for Bernoulli and corresponds to those parts of the member where the assumption for Bernoulli can be accepted. For example, the assumption is accepted for the analysis of long beams loaded in bending, where the load transfer is continuous over long distances. Cracks and compression struts between the cracks are parallel to each other over the whole region. D stands for discontinuity and corresponds to the regions where the assumption of Bernoulli is no longer valid. This is typically the region around two parts. One is a geometrical discontinuity, which considers the changes in cross-section, openings, nodes in frames, connections between girders and beams. The other one is a statical discontinuity, which considers isolated loads, supports, temperature changes, anchorage of pre-stressing tendons. Although the strut and tie method may also be applied in B regions, it is above all the method to be used for the design of D regions. Strut and tie models are helpful tools to design the necessary reinforcement, which helps to arrange the transfer of loads through the D regions towards the B regions. A suitable truss model has to be identified for the design calculation. However, in order to find a solution which meets the serviceability limit state requirements, avoiding excessive crack width, the chosen truss system should be as much as possible in agreement with the real stress state situation according to linear elasticity theory, lower bound theorem for plastic methods. The ideal situation is that the scheme of principal stress trajectories would be known. The stress trajectories show how the imposed loads are transferred throughout the structural member to the supports. This slide illustrates load paths of a simple supported beam, a cobo, and a wall supported by 2 columns. The analysis allows to identify the strut and tie model, which has to assure the internal equilibrium of the member for the imposed loading conditions. In most cases, the aim is to identify a statical determinate system, which allows the determination of the tensile and compression member forces by means of equations expressing the equilibrium of the nodes in the truss. Traditional strut and tie models are shown in this slide. The tensile forces in the ties have to be taken up by reinforcement bars. The reinforcement may be composed of several bars which are oriented according to the axis of the tie in the strut and tie model. In order to prevent surface cracking, additional reinforcement may be necessary, such as links and technological reinforcement. However, these traditional strut and tie models are not optimal models, and increase the required steel quantities of reinforced concrete structures. To address this, I will introduce truss layout optimization to obtain optimal strut and tie models. Truss layout optimization using the ground structure approach provides a fully automated means of identifying near optimum truss structures. The minimum volume truss formulation is used. The objective is to minimize the volume or weight of the structure. The equilibrium constraint is a joint equilibrium matrix B times a vector of internal member forces Q equal to a vector of external nodal forces F. We consider a frame ABC comprising 2 bars, AB and BC, with pinned supports at A and C. Assume the bars are oriented at an angle theta to the horizontal. The equilibrium equation can be rewritten. Considering a bar AB structure, the relevant yield constraint shows in this slide. The cross-sectional area of the member is not fixed and is a problem variable. The area AAB is larger than 0. Finally, the new objective function is to minimize the total volume. For a problem comprising M members, where AI and Li respectively are the areas and lengths of a given member I. The standard layout optimization involves 4 steps. Firstly, the design domain, load, and support conditions are specified. Secondly, the design domain is discretized using nodes. Thirdly, these nodes are interconnected with potential members to create a ground structure. Finally, an optimum layout is identified by solving the optimization problem. Now we can use this method to optimize work examples. It should be noted that in many cases, it is possible to draw a workable approximate scheme of load transfer without the knowledge of the exact linear elastic stress trajectories. In the previous cases, we can use truss layout optimization to obtain the optimal truss models, which can be efficient and convenient to present the load paths. Next, we can use 2 examples to illustrate the applications of layout optimization in reinforced concrete structures. The first example is a D-beam with openings. Reinforced designs can be obtained with truss layout optimization for complex domains. The minimum volume or weight design, in this case, results in a reinforcing layout that doesn't require stirrups in the confined space under the hole, simplifying construction. Optimal model shows that there is tension in the lower left corner of the beam below the cutout, which could result in splitting cracks from the corner of the hole to the edge of the beam. A designer may miss this potentially detrimental behavior with a traditional strut and tie solution. The second example is a hammerhead bridge pier. Hammerhead bridge piers are widely used and typically designed with the traditional truss model. Vertical shear stirrups are spaced evenly across the pier cap, with a top mat of reinforcing steel control cracking at the girder bearing line. The minimum volume or weight truss model demonstrates that for the loading case considered, the shears the rubs don't coincide with the internal tensile force trajectories. Instead, jabbed reinforcing steel or post-tensioning would be a more appropriate design solution. From conclusions, what we learned? By analyzing the stress distribution and load transfer paths, strut and tie models can make the complex concrete members transform into a simple structure and a clear truss model. Truss layout optimization provides an effective and convenient method for obtaining optimal strut and tie models. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.